Está cargando, ya está transmitiendo, en unos segundos debería de empezar a verse en YouTube. Y con el retraso, o sea, todo lo que yo voy diciendo ahora ya se ve. De hecho, ya ha entrado más gente a la charla, 6 personas.
6.
Y ahí
De momento
os recomiendo silenciar.
Voy. Ay, ¿qué ha pasado?
No a los espectadores, sino a los que estamos emitiendo ahora mismo. Para que no haya interferencia entre...
Mira, está Verdú.
Sí. Buena Verdú. Qué internacional esto.
De un extremo a otro. Buenos días, Verdú. Allí será muy temprano, ¿no?
Hola, Alberto. Bueno, Chisco y yo vamos a salir de la sala ya y Esther, tú cuando quieras, empieza, porque esto ya está emitiendo.
Perfecto. Si os parece, esperamos unos minutillos, damos los 5 minutos de cortesía por si hay alguien que está intentándolo y enseguida empezamos. Bueno, yo creo que ya le hemos dado los 5 minutos de cortesía, así que si os parece, empezamos. Bueno, en primer lugar, muchas gracias a todos y a todas por conectaros esta tarde para celebrar el Día Internacional del Color. Muchas felicidades a todos, que supongo que los que estamos ahora conectados somos gente que estamos trabajando directamente relacionada con el color. Por eso, enhorabuena y os animo a seguir trabajando en este campo dedicado a ciencia y tecnología o percepción del color. En segundo lugar, muchas gracias, Jalil, por aceptar esta propuesta y ser tú el primero en iniciar, como ya te hemos comentado, en iniciar este ciclo que esperemos que podamos continuar celebrándolo en el futuro, pues eso, para celebrar este Día Internacional del Color, pues qué mejor que pues hacerlo mediante alguien de nosotros que esté trabajando en este tema y que nos cuente pues, su último trabajo, su última investigación desarrollada. Para aquellos que no conozcáis a Jalil, voy a hacer una breve presentación. Jalil Urabait ahora recientemente trabaja en un nuevo departamento, el Optometry Department, de Arab American University en Palestina. Durante estos últimos años fue miembro del grupo de visión y color de la Universidad de Alicante durante los últimos 5 años, donde realizó su tesis doctoral que llevaba por título Advanced Digital Reproduction of Goniochromatic Colors. Inicialmente realizó sus estudios en la Universidad de Granada, donde realizó el grado en óptica y optometría, y además también realizó el máster Erasmus Mundus, denominado Color in Informatics and Media Technology, conocido como CIMET, y que ahora no se denomina así, pero que sabemos que es un máster con mucho prestigio. Pues como he dicho, pues eso es uno de nosotros que trabaja en ciencia y tecnología del color, donde sus intereses pues, son ciencia del color, tecnología, desde un punto básico de la investigación aplicada y sobre todo pues eso, pensando en esas aplicaciones industriales. Como he dicho, pues va a contarnos pues en este caso su última investigación, que principalmente es su tesis, donde hará un resumen para que todos la conozcamos. Muchas gracias nuevamente, Jalil, y a todos y todas vosotras por participar esta tarde. Os animo a que uséis el chat de YouTube para ir preguntando o hacer comentarios sobre la conferencia. No es necesario esperar hasta el final. Si queréis, vais comentando las dudas o comentarios o cuestiones en el chat. Nosotros las iremos recogiendo para cuando luego Jalil ya termine la charla, pues si es necesario y oportuno, pues generar un pequeño debate, cuestiones o comentarios acerca de esta conferencia. Así que por mi lado nada más. Cuando quieras, Jalil, pues presentar y gracias.
Muchas gracias, Esther. Muchas gracias a todos los que estáis. Bueno, es un placer estar aquí, especialmente teniendo a gente de Granada. Y voy a compartir pantalla mientras. Share screen. Ok. Vale, eso decía, muchas gracias y es un placer estar aquí teniendo gente de Granada, donde empecé digamos, esta aventura y luego en Alicante y, bueno, teniendo a maestros míos que os voy a contar, pero bueno, primero, siempre se puede aportar algo. Desde que llegué a España siempre me he ido con la idea de volver a Palestina y aquí estoy con todo lo que he aprendido en Granada, fuera, en Francia, en Bélgica y luego en Alicante, pues con todo lo aprendido he llegado a este punto y aquí estoy en Palestina, en un departamento de óptica, como ha contado Esther, y bueno, contento de tener los hilos y la conexión con España de nuevo. desde la distancia y contento de estar aquí en mi tierra ayudando y a ver si puedo aportar el granito como se dice y teniendo en cuenta la situación especial que se vive en este país, Palestina. Pues muy contento de estar aquí de nuevo y procedo con la charla. Voy a hacerla en inglés por si acaso se conecta alguien y además eso, los términos y tal los tengo más controlados en inglés. Pues good evening, or here's good evening, maybe good afternoon in Spain. So the talk I will give today is titled Improved Reproduction and Visualization of Effect Pigments. So as Esther mentioned, so this was part of the research I did during my PhD studies in Spain. So this is the content I will follow. This is the content I will follow the outline in this presentation. So first, a brief introduction about the effect pigments, effect coatings, goniochromatic effects, and also the digital reproduction and what we mean with digital reproduction, especially focused for these kind of effect pigments. Then the objectives of this work, why we did this research, and after that, there are two main sections, the visualization of effect pigments. So here we focus mainly on the displays, the visualization systems. And the second part is focused on the rendering of effect pigments. So the softwares and the physical models we use to make a representation, digital representation of these effect pigments. Then the future perspectives, the continuation of this research work, and finally the conclusions. So, talk about effect pigments. So these are new, innovative materials. They come with impressive visual appearance and we can say unusual visual appearance. They are also called goniochromatic colors or goniochromatic pigments. So this means that they change, or the appearance of these pigments change with the observation and the illumination angle. They have become very popular. They are widely used nowadays due to these impressive appearance they have. So they become highly popular in the markets, like, for example, in the car painting, cosmetics, and many other applications. So in order to study these kind of pigments, so there are two main attributes that we should focus on. The first is the color and the color shift, which also called goniochromatism. So that the color changes when we change the illumination or the observation or measurement angle. And they are also special due to the special texture effects they produce, which are the sparkle and radiance mainly. And we will focus on these three effects. So if we come to the literature, so we can find like different classification of effect pigments, but we decided to split them and to follow one of these classification where they are divided into two groups, the metallic and the special effect pigments. So almost all of them, they are composed of flake-shaped particles in lamellar forms, which give them this special appearance. Okay, so if we compare them with the traditional absorption pigments, so light enters and interacts with the pigment particle and is dispersed in all direction, and that's why we see a kind of uniform color, or what we can also call solid color. in the second image here in the middle, so we have a representation of a special effect pigment. So with multiple layers, light enters and is reflected in, it suffers multiple reflection, which causes a pale kind of appearance. In the third image here, so this is structure of metallic effect pigments. So light enters, interacts with these, in this kind is aluminum flakes, okay, and is reflected directionally in a certain direction, depending on the orientation. So in order to study and to characterize the appearance of these effect pigments, so we have to study the color and also the texture effect. And as I mentioned before, we focus on the sparkle and graininess texture effect. So what is sparkle? What's graininess? So the sparkle here, these are car paints, but these are small panels. We achieve them from AkzoNobel. So AkzoNobel is part of this research work together with the CSIC, the National Optical Institute from Madrid. So the sparkle is seen under directional illumination. We can say kind of sunny day where intensity spots with light intensity, highlight intensity are seen, as you observe here. For example, if we compare the left panel to the right panel here in the display, so the left panel shows more sparkle than the right panel. The graininess is seen or observed under diffused illumination, some kind of overcast or cloudy sky. So the appearance here, the graininess is a kind of orange peel texture, or what's also known as the salt pepper effect. So as I mentioned, the appearance of these kind of pigments is dependent or strongly dependent to the observation and measurement or and the illumination angle. So this goniochromatic effect makes them complex. So it's, if we want to physically describe these pigments, so this is not easy, and we need a kind of BRDF. Okay, so this is a bidirectional reflectance distribution functions. So basically, these functions give a huge amount of illumination and measurement in all directions. So, for example, we have the goniospectral radiometer, the Jefe, which was developed in Madrid, in the CSIC of Madrid. So it gives a kind of complete BRDF with a huge amount of illumination angles, huge amount of measurements also. So this is the bidirectional illumination and measurement, and also out of plane measurements. Okay, so but this huge amount of data is not practical when we go to industrial applications. So for that, we come, or the industry, they come with reduced or more compact devices like the Big Mac Eye, which measures 6 different geometries in plane with fixed illumination. So this is widely used in the car painting, and it deals with a reduced, we can say a reduced BRDF, and still give an acceptable approximation for to describe the appearance of these effect pigments. It also gives information about the sparkle and also the graininess. So, having into account this complexity, the physical complexity of these kind of pigments, what if we want to make a digital simulation, digital visualization of this pigment? So we know to make a digital simulation of real objects not easy, and this is much more complex when we talk about effect pigments. So digital reproduction is part of our daily life. So it's present in gaming, cinema, and film production, online shopping, and advertising, and also in virtual reality, which is very common in all fields now. And there are many rendering softwares like the Maya, Keyshot, Mental Ray from NVIDIA, and they are all claiming photorealism. Okay, but they come with impressive colors, impressive images, but we should differentiate between photorealism and accuracy. So these are impressive and realistic images, but for some specific application, they are still not enough. Okay. Another important part is the display. So we make a physical model, we use a digital rendering software, and at the end, we need a display to show what we get. Okay, so the display is very important, and unfortunately, the currently available displays are still showing limited color gamut. And when we talk about some critical applications like for example, the automotive design where effect pigments are used, so the color accuracy provided nowadays is not good enough still. So you can imagine the challenge here, because we do need a good display and a good rendering approach in order to have an accurate simulation of effect pigments. So for that, we focused on improving the digital production of effect coatings by first providing an enlarged color gamut. So this is about the displays, and secondly, providing an improved rendering framework for accurate representation of effect coatings, including physical models, so accurate physical models to mimic the behavior of these pigments. So, as I mentioned at the beginning, the core of this research is divided into two sections. The first focusing on the displays. So, this part of the work is published on this peer review article published in the Color Research and Application titled A Multi-Primary Empirical Model Based on Quantum Dots Display Technology. So we went to the market, we did a screening looking for new technologies, and we found these quantum dots display. So they claim that they come with improved and enlarged color gamut, and also sharp emission of the channel and the RGB. So for that, we decided to start to study this display and to see their behavior for the reproduction of effect pigments. And from that, we decided to go further and to try to build a multi-primary model to increase the color gamut. So at the beginning, we needed to characterize this quantum dots display. So we did color and spectral calibration using the gain offset gamma famous and conventional model for the calibration of display. So it's mainly used for CRT, but it's still valid for other new technologies, but under certain conditions. So the gain offset gamma mainly studies the relation between the signal given to the RGB channels and the lightness produced by these signals from these channels. So through this transformation matrix where these three stimulus values for each channel are the three stimulus values for each channel, but at the maximum emission. These are GB are the luminance produced, and it's equal to this equation where G is the gain, D is the digital count. So this is the signal we give to the channel, and gamma and this is the gain and gamma. So these parameters, we will use them to evaluate the OETF curve, which will we see it later. So in order to be able to apply this GOG calibration model, there are three conditions that should fulfill. So the first is that the electro-optical transfer function behavior should match a power curve. So with the gain and gamma, we will try to find the fitting curve, and this fitting curve should match a power curve. There should be a primary constancy and also luminance and three stimulus additivity. So we will study this, or we studied these three conditions one by one. So to be able to do that, we selected this commercial Philips Brilliance LCD quantum dots display. We generated stimulus, okay, so 18 stimulus per channel, starting with low intervals, and then for the high digital counts, digital levels, so the interval was 25. So we showed 18 stimulus per channel with additional 2 white and black stimulus, and we measured them one by one using the telespectral radiometer Konica Minolta. So here's a representation, spectral representation of each one of these stimulus. Okay, so here the 18 measured for the blue, for the red, for the green, for the red. The black one represents the white measured. Okay, so with this equation, so this is equivalent to the RGB. So for each channel, we do know the digital count. So this is what the stimuli we give, and by performing the fitting, we were able to obtain the gain and gamma values, and we found that the AOTF fits a power function as you see here. So the fitting was very good, and with these gain and gamma parameters, we will be able then to build the complete GOG model. The second condition was the primary constancy. So we represented each one of the stimulus for each channel in the CIE diagram, and there were no constancy as you see here, but we realized that after black correction, because the black on the display is not completely black, so there's still emission. So after black correction, we do have a good primary constancy, still acceptable for the red channel case. So this is the second condition. The third was the luminance and stimulus additivity. So that's basically comparing the white three stimulus values to the sum of the RGB values. So as you see here, we do have small differences, and that was the same for the luminance. So we do have a luminance and three stimulus additivity. So the three conditions were fulfilled. So then we are sure that this characterization model, this calibration model, the GOG, is valid for studying the behavior of the quantum dots display. So, and this is how the transformation matrix of the GOG model looks. So by knowing the digital counts, the signal I will give to the display to each channel, we are able to predict the resulting color. And also we did a validation further step, another step validation step. So we generated 16 different images with combination of the 3 channels, and we evaluated the computed color to the measured color. By computing the color difference, we found that the average color difference, delta E, was 1.39, which is still less than 2, and this is the critical color difference, or used mainly in the digital graphics can say domain. So this is still acceptable and shows good results. We also performed a study of the luminance and the chromaticity, the uniformity of these luminance and chromaticity along the display. So we measured 9 different spots, and as you can see, so here we show the error, the mean root square error. So for the luminance, we do have some kind of high errors, but this was much better. So the display shows better uniformity in terms of chromaticity than luminance. Okay, so we wanted to see how this display performs for the digital reproduction or for the reproduction of effect pigment. So we needed to evaluate the color gamut of this display. So by comparing the color gamut of the Philips quantum dots to the International BT 2020, so we found that it covers almost 81% of the International Standard 2020, which is good, but there are still lakes here. So, for example, in this yellow and cyan or blue regions, so they are still not covered. So we will face problems when for showing vivid blue and or cyan and yellow color. So we decided to go further by proposing 2 additional primaries, one cyan, we called it, and the second is yellow, in order to cover these regions. And this is what we call the multi-primary model. So the display will have the RGB with 2 additional primaries or channels. Okay, so to do that, we first model the RGB curves. Okay, so we use the Sigma plot software, and we found that this equation shows a good fitting for all channels, the RGB channels with a good fitting. So we will use this curve to build the RGB by C model. So how to select these yellow and cyan additional primaries? For that, we built an optimization route. We gave it 2 conditions. The first is that the resulting white should match a D65 white with these chromaticity coordinates, and also we needed to improve and increase the luminance. So the second condition was that the luminance should be higher than 500 candelas per square meter. And we gave to this optimization route 2 degrees of freedom. So it looks for the lambda, the peak lambda C, and also the height B. So if we come back to the equation, so the parameters here, the A is a constant, the B is the height of the curve, C is the wavelength, D is the width at half maximum, E is related also with the width. So the parameters here, the freedom degrees, where the C, the peak wavelength, and the height. And after running this optimization route, we end up with these 2 candidates. for the yellow and the cyan. And if you focus here, so you see the RGB with the two proposed additional cyan and yellow, or it could be, we could call it also orange primers. And these are the coordinates of these RGB YC primary channels for our model. And now, so thanks to using the GOG simple, can call it simple calibration model, so we could use an extended version of this GOG model by adding the yellow channel and the cyan channel to the transformation matrix. So here we have the yellow, we have the cyan, and here are the luminance components. So with this model, we could study the behavior of this multiprimary model. So we come again to the color gamut. So by evaluating it the same way compared to the International 2020. So as you see, this is the International 2020. The dashed is the Philips RGB quantum dots, and this one is the extended multiprimary model with the cyan and yellow model. So as you see just in the graph, so we gain area on the gamut. So if we compare the gamut area now, so as you see, we increase the gamut area compared to the International 2020. So if the quantum dots RGB covered 81% of the International 2020 standard, so the RGBYC, our model now covers 90% of this international standard gamut. We also did another or further evaluation by studying the gamut volume. So here is a representation of the gamut volume of the RGBYC, the multiprimary model, in red, and the black one shows the Philips quantum dots RGB display color gamut. So what we did is that we selected a set of gonochromatic samples, and we make them represented here in the same graph. So as you see, the RGBYC gamut is enlarged, so the Philips quantum dots still inside the multiprimary gamut. And if we take one luminance level, so as you see here, many samples were just in the border or outside the quantum dots RGB volume, but they are now covered by the gamut volume of our proposed model. So to summarize, we increased the color gamut by introducing these two primary, yellow and cyan. We improved also the lightness, so it reaches almost 130 units. We achieved better reduction, or we expect to achieve better reduction of vivid yellow and cyan colors. The proposed approach stands out for its simplicity, so we still use a GOG model and a simple 4 parameters model. So this will allow us to make further studies, further tests with different primers configurations. So now we come to the second part, which is focusing on the rendering of effect pigments. So the rendering softwares and also the physical representation of these effect pigments. So this work was published on these two articles. The first is published in the Journal of the Optical Society of America. The second was published in the Optics Express. So with ExxonMobil and the TC again, and where I was in Alicante, so we decided to build a 3D real-time rendering framework dedicated for the reproduction of effect pigments. So this tool comes with many novelties. The first is that it runs in an iPad tablet computer, so there were no need for potential computers with high memories and high potential graphic cards. The second is that this real-time rendering framework comes with a fully spectral approach. So we use 16 different spectral bands to represent the whole measured spectrum of the colors. It also supports physically based representation. So we used a kind of flake-based model to represent the BRDF. And it also, what is also important is the illumination. So in order to have a controlled environment, controlled illumination, we decided to start by building a simulated light booth. So following what we do in the lab, so we use controlled illumination light booth. So we decided to build first a virtual light booth inside this framework. We also used a mobile display characterization and illumination model, the MDCIM, which comes with improvements compared to the sRGB model, and was specific for this kind of display. So the calibration it was much better. And at the end, so this is also a novelty of this work, we were able to perform visual validation, so visual evaluations comparing the real sample inside a real light booth to the virtual sample inside a virtual light booth on the display of the tablet. So we started by making a physics-based simulation of the light booth. So we selected the bicospectral effect light booth, which is widely used in the industry and also in the automotive domain. So we started by building a 3D model using Blender. As you know, so the BICO supports 6 different geometries, 6 different observation geometries in order to see to evaluate the color shift. So we modeled one visual model for each of these geometries, and these are the same as the measured by the Big Mac eye. So in order to make a good characterization of the light inside the light booth, so the light intensity coming for each direction, so we need the light distribution profile. So this is usually done by the manufacturers. For example, for the light tube presented on the bicospectral light booth, so these are files called IES, Illum data files, but this unfortunately was not available for the light tube used in the BICO. So for that, we decided to make a model to find the light distribution. Okay, so for that, we decided to measure the luminance on the object table in different positions. Okay, and by assuming that we have a Gaussian distribution, we were able to compute the intensity, the luminous intensity coming from this light tube at each direction. And by using this Hertz algorithm for sampling the light source, so we were able to sample this light distribution on the digital GGX distribution model. So this is inside the rendering model. And we also had to care about the spectral distribution of this light. So we measured it for all geometries, but as you see, there is no difference here. So, and we also need to characterize the cabin walls, since we will have effects from the surrounding on the observed object. Okay, so we measured the spectral reflectance in different points of the inside of the light booth, and we found that this matches a neutral gray. So we had to model these also, and at the end we come with this virtual bicospectral effect light booth. So this is a screenshot from the iPad, the tablet. Okay, so as you see here, so we represented the platform, the lighting, the light tube. This is the visualization slit. So for who do not know the bicospectral light booth, so the object is placed here in the center, and you can switch the move the platform, the illumination is fixed, and the observer is placed just in front of this observation slit to observe, evaluate the sample we have. So here we're able to visualize, to simulate 3D objects, and as you see here, the reflection of the light, so it's pretty realistic, and this is what the observer could see from the observation slit. And here's also a simulated color panel inside the light booth, the virtual with colors. Okay, so we then started by using a full spectral approach. So we used 16 spectral bands in order to simulate the color. Okay, so from the spectrum measured with the Big Mac eye, we were able to simulate the color of the sample. So here we're still talking about color only with no texture yet. Okay, so we decided to study the validity, or to validate this full spectral approach. So for that, we decided to do the visual experiments. Okay, so the samples were measured with the Big Mac eye, always at 45 as specular 45 degrees, since these are solid paints. So we do not expect that they change their color with the geometry. So that's why we use fixed illumination and also observation geometry. And this is the validation setup we use for the visual assessment. So as you see here, so the observer is placed in front of the slit lamp, the light booth. We placed the tablet just next to the slit, and on the tablet you see the virtual sample inside the virtual light booth, and inside the light booth, the real one, we have the real sample, and we could evaluate flat or curved or 3D objects. So we then came to this question, so how we evaluate this matching? So we decided to use two different methods. The first is the scoring methods. So observers give a score between 0 and 5. So if they give a 0, so that means that they see no difference. So we have a full matching between the real and the virtual sample. 5 means a large difference, very bad matching. So we are seeing completely different colors. The second was the grayscale method. So the observer evaluates the difference between the real and virtual sample and and compare it to one of these gray difference from the gray scale. So for this evaluation, as I mentioned, so we obtain these solid colors, solid paints from AkzoNobel. So they are commercial colors. So we had a bigger set. We selected only 30 solid color samples. 16 observers performed this experiment. They are all with normal color vision, normal and corrected visual acuity, in a dark room, as always, the fixed illumination and also observation geometry. They all did 3 repetitions, and we used, as I mentioned, the scoring and the grayscale method to compare between them, and we tried to cover like a wide range of colors when we selected these samples. So after collecting the data from these 16 observers, so we studied the intra-observer repeatability, the inter-observer reproducibility, and we found a good value. So these are low values, so we can rely on these answers from our observers. So here we have the results. So this is a representation, box plot representation for the grayscale and the scoring method. So here we have the samples 1 to 30, and this is the grayscale, and here are the scores from 0 to 5. So what we found is that the average color match given by the observers using the grayscale was 4. So G equal 4. So some kind of this, I guess it's visible in the screen. So this is the average difference that they found. And this grayscale value equal to 4 is equivalent to a color difference of 1.6, so which is still less than 2, the value usually used in the digital production domain. In the case of scoring method, so the average visual score from all observers was 1.78, so this was between the small negligible difference and the difference visible but still acceptable. So these were good results, or acceptable results, we could say. So if we evaluate the percentage of acceptance for the grayscale, so this was 77% of the samples were accepted. With the scoring, 80% of samples were accepted. So as you see, we see different similar perform using the 2 methods. Okay, and when we study the rejected samples, so we found that they are all almost fall in the 4th quarter, and we think that this is more related to the display itself, since this kind of mobile display has always this blue effect. So now we see that the full spectral approach is working properly, still give acceptable values, acceptable results, and from that we go forward, and we decided to start with metallic paints, with effect paints. In this case, we focus on metallic paints. So for that, we use we need the measurements from the Big Mac Eye. So we need the angular distribution of the spectral, the BRDF of this effect coating. So the Big Mac Eye gives the reflectance, sparkle parameters, graininess, and we could also compute the flow. Okay, we also used a flake-based parameterization model to interpret the BRDF measurement for all the required rendering geometry. So this flake-based parameterization works well, and it comes with this characteristic that it counts for the flake itself. So it counts for the orientation and also the roughness of the flake itself, and not on the substrate or the reflection of the substrate. So it gives better representation of the BRDF. We used also the GGX microfacet model. So this model is widely used on the graphic representation. Okay, so it has different parameters like the surface roughness of the clear coat, the flake orientation, also the distribution, as well as the non-flatness of the flake itself, so the roughness of the flake. So with this model, we will be able to make sampling of the BRDF from the flake-based parameterization to show or to make the digital representation of these effect pigments. So the GGX microfacet model comes with many parameters, but these three were the most important, or I can say the most relevant in our case. So by changing manually these three parameters, the flake area magnitude, Fa, the roughness metal, Rm, the roughness flake, RF, so you could introduce texture to this solid color. Okay, so the texture is characterized by these three parameters inside the GGX microfacet model in our rendering tool. But what we have is measurements taken by the Big Mac, the Big Mac Eye instrument, which gives the spectrum, the CIELB, the sparkle and graininess factors, and also the flow. So we had to find a way to find a correlation between these measurements from the Big Mac Eye and these three model parameters. So the idea is that just with taking the measurements with the Big Mac Eye, I give this information and finding the correlation. This correlation will find these three parameters. So for that, what we did is we tried to match these three parameters to the measured parameters. So first, we did a perception-based rendering. So we selected a set of metallic samples, okay, and one by one, and by manually adjusting or tuning these model parameters, we tried to match the texture of the metallic paints placed inside the light booth, and we have the virtual sample. So we tried to match the virtual sample texture to the real sample. So this were done for 30 samples, and 2 experts in color did this matching. So we have values for each one of these 30 samples, which was done, the matching was done manually, and we have also the measured from the Big Mac Eye. Okay, so by using a matrix adjustment method, so this matrix where M is the model parameters, the 3 model parameters, B is the measurements from the Big Mac Eye, and A is the adjustment matrix. So the idea is that I give these parameters, we should find this A matrix in order to obtain the 3 texture parameters. So this will make our model automatic or automated. We measure and directly we have a texture representation on the virtual representation or the virtual simulation. So for that, we built an optimization route in order to find the most relevant Big Mac Eye parameters. So we have a large set of parameters measured by the Big Mac Eye, and we look for the combination of these parameters, giving the minimum average relative error between the measured and the computed model parameters with this matrix. And from that, we find that these 6 parameters are having the minimum, So we found that these parameters were giving the minimum error. So and the A matrix obtained was this one. So now, just by measuring the sample and giving these parameters to the model, directly we obtain the 3 model parameters to represent the texture. And this was the results we have. So this is just an example of a metallic paint curved one showing on the digital production framework we built. So we need to validate these results. So how accurate this model is. So we first evaluate the color and then the texture. The same, we had a large set of metallic paints from AkzoNobel from the Netherlands. We selected a reduced set from this large set. Again, we used the Big Mac eye, and we started by 2 initial tests to evaluate the color flow at first. So at this point, we are not showing texture. We wanted to see that if the full spectral approach is still working with this texture rendering approach. So we started by 2 initial tests. First, in flat samples, as shown here, and secondly in curved samples. So we wanted to see how it performs in for 3D objects. Okay, and at the end we performed a final test including color and texture. So that means that we evaluate the total appearance. Okay, so in the 2 initial tests, as I mentioned, we evaluated the color flow, so different geometries now, but using flat and curved samples with no texture yet. So the real sample has texture, but the simulated sample does not show texture yet. In the final test, we included the color and texture. For this evaluation, we used only the scoring method. So we saw that the scoring and the grayscale, they show similar behavior, and the scoring was more reliable. The grayscale, people or observers show like dots when they use it. So how to compare color with gray differences? So it was a bit confusing for them. For that, we decided to continue with the scoring method. So the first was with 15 metallic paints, only 5 observers, because that was just directionally the study. In the second, we used curved samples, and in the final test, so here we evaluated the color and texture. So we extended the number of samples we used. We used curved panel, 15 observers, and here we evaluated only one geometry, because in this first and second test we evaluated already the color shift. So here we wanted to see the more about the texture or the overall, but since we use curved panels, so the curves already induces this color shift effect with the different geometries. So if you observe here, so we do have a representation of the color flow. So this is the same sample at different geometries, 25, 45, 110. So it goes from light, I don't know, brown to dark brown. And also this is with curved samples. So as you see, going from a specular -15. So here the color was clear cyan. So as we switch between the to that 15, 25, 45, 75, 110, so we go to a kind of blue color. And this is representation of the virtual simulation of a real sample. So this image is the real image taken by the real sample. taken by a phone camera, and this is the virtual screenshot for the representation of this real sample. So as you see, we do have, I can say, very good simulation. So this image is not that accurate since it's taken by a mobile phone, but in real world, the matching was even better than what you see here. So again, we studied we did a statistical analysis. So we studied the inter-observer repeatability and inter-observer reproducibility for the 3 tests for the answers, the data obtained from all observers, and we still have low values. So these are still less than 1 unit of the scale, the scoring scale that we use. So this tells about the accuracy. I can say that I don't say the accuracy, but the validity of these data obtained from the observers. So coming to the acceptance range for the first test with flat samples with no color, so we had 80%. With curved samples only color, so we see that we have an increased acceptance percentage, reached 93%, and we think that the curved object already included a certain we can say chromatic effect. So this might help on seeing this color and gives better matching. In the final test with color and texture, the total appearance, so we obtained 90% of acceptance, and that was very good result. So if you see here is also a representation, box plot representation of the evaluation given by the observers for the 30 samples. So here we are talking about the final test, the overall appearance. So we had an improved acceptance. The average visual score was at 1.46. So this is more near to the negligible than the acceptable. So to summarize this second section, so we here built a physically accurate representation of a global illumination. So these are the light booth we built by using the mathematical matrix adjustment method. So this allows us to predict the GGX model texture parameters. So somehow we have an optimized automatic representation. So by just measuring, we drop these measurements, we obtain the texture parameters. Okay, so we also obtained a high accuracy for the representation of color and also texture, as you saw. So we had a acceptance percentage of 90% for the total appearance of effect coatings. We also saw that observers mainly relate the non-matching sample to deviation in color, but not in texture. So this could be also related to the limitation of the display we use, the display of the tablet. So future perspective, so how we could improve and continue with this work. So first, talking about the primary model. So we could improve the multi-channel model by better selection of the additional channels. For example, we could achieve further optimization of the accuracy of the rendering. So this may be achieved by improving the representation of the colorimetric properties of the display. So we use the tablet display. We could use a quantum dots display, which comes with enlarged color gamut, and we could go for further improvement by using a multi-channel display. So if now we get 90%, we expect to have much better acceptance value if we use a more potential display. Further improvement is expected when a larger set of sample is used for the computation of the GGX model parameters, so we can still find a more optimized model to compute the GGX model. The parameterization and interpolation of the BRDF may also be improved. So these physical models for the representation of the behavior of these metallic paints, so these also could be improved. There are many groups working on that. This rendering framework have been designed to allow using data from any other combination or measurement geometry. So we can use different measurement devices, and the algorithm, the framework is built in a flexible way. So we can use different instruments, different data in order to see how it performs. So finally, to summarize the conclusion, so the available quantum dots display technology was found to provide an improved representation of colors. This was not enough to cover the wide variety of colors and effects produced by goniochromatic pigments. By taking advantage of the quantum dots technology, a multi-primary channel display model was developed, which guarantees a better reproduction of effect pigments. In this research work, so we provided an accurate digital simulation of effect coatings on simple tablet display by developing a full spectral and also physically based rendering approach on a simple iPad tablet computer. The visual evaluation incorporated the high color accuracy of the rendered images. And at the end, I would like to thank AkzoNobel, the TC, University of Alicante, and also the Ministry of Economy, Industry, Competitiveness for their for the scholarship. I have to perform all this work, and thank you for all for being here after this large day of working.
Muchas gracias, Jalil, por esta charla, por esta presentación. Yo no voy a decir nada sobre el trabajo porque lo conozco en primera persona, ya sabe mi opinión sobre ello. Ha sido una tesis, pues, desde mi punto de vista muy completa, porque he tenido pues, muchas partes. La parte más de experimentos visuales, la parte del modelo. O sea, que en este sentido creo que has trabajado y que hoy además lo has sabido exponer y transmitir muy bien. Creo que hay alguna pregunta en el chat. Hay un poco de retraso entre lo que yo hablo y lo que se recibe en el chat, o sea, en el YouTube. Si hay más preguntas, ahora es el momento. Por el momento tenemos una de Francisco Miguel Martínez Verdú, que te pregunta que por qué no has evaluado el grayness con las muestras planas.
Vale, ¿por qué no hemos evaluado el grayness? Lo que hacemos es evaluar the total appearance. So, podemos hacerlo en el futuro. Tenemos el modelo y a partir de ahora podemos centrarnos en un efecto por sí solo. So, se puede evaluar grayness, sparkle. El modelo es flexible y se puede trabajar más en ello. Por ahora, porque el modelo no te da control claro por ahora para controlar el sparkle por sí solo y el grayness por sí solo. So, lo que te da es la textura. Se puede trabajar más a profundidad, igual con el GGX model, trabajando más en los parámetros que tenemos, identificar los parámetros que afectan más la reproducción de sparkle y cuáles afectan más la reproducción de graininess y centrarnos en un efecto o otro por separado. Pero por ahora a lo que nos ha dado el tiempo, hemos llegado a estudiar y evaluar la apariencia en total, digamos. Pero eso sí, que se puede hacer. Hace falta un poco más de trabajo para identificar los parámetros que tienen efecto en cada texture effect y a partir de ahí se puede estudiar cada uno por separado.
Muy bien. No sé
Gracias,
si
Verdú, por estar aquí hoy, que también es parte de tuya, este trabajo, o tuyo.
dice que gracias. No sé si hay alguna otra pregunta. De momento no. Pregunta, comentario, algo que queráis comentar con Jalil. Bueno, pues si no hay más preguntas, que parece ser que de momento no hay nada más, pues lo dejaríamos.
Creo que Francisco pregunta aquí en el chat, pero en un chat interno, no en YouTube. ¿Por qué no se le envía por YouTube? Vale, lo leo yo. Dice, impresionante trabajo, gracias. Enhorabuena, gracias. Y sabes si empresas del sector como Big Gartner o otras han mostrado su interés en potenciar la reproducción virtual de pigmentos de efecto. Me refiero a si realmente lo ven como una línea potente de desarrollo o si por ahora prefieren centrarse en la medida física. Medidas instrumentales. Igual la ha respondido Tisco, la ha respondido tú. Yo creo que están más interesados en las medidas físicas por ahora. Pero, por ejemplo, empresas como AkzoNobel sí que les interesa. Y hemos estado trabajando con ellos no solo los 5 años que llevo yo, sino desde antes, porque al final el producto lo que van a vender ellos es la pintura y tienen más contacto con clientes habituales en la calle o donde sea. Pero Big Gartner, el contacto que tienen más con empresas que trabajan, que fabrican, laboratorios y tal. Entonces, yo creo que es eso lo que pasa. No les interesa, se centran más en las medidas físicas, caracterización física, pero empresas como AkzoNobel, que sí llegan a los customers, sí que les interesa este tipo de reproducción digital. Sí.
Creo que ahora, si no hay nada más,
De nada.
diría que no. Pues eso, otra vez reiterar nuestro agradecimiento por parte del Comité del Color a Jalil Urabait por acompañarnos esta tarde y compartir con nosotros su trabajo. A todos y todas las que os habéis conectado esta tarde para celebrar este Día Internacional del Color y, como he dicho al principio, pues esperamos que este ciclo o esta conferencia que iniciamos con motivo de esta celebración del 21 de marzo, pues que consigamos mantenerla en el futuro y que al año que viene pues tengamos otra charla relacionada con el color. Y nada más, por mi parte, lo dejaría aquí y eso. Muchísimas gracias a todos y todas.
Muchas gracias, Esther, y a todos, y Happy Colors Day.